We're going to do a reciprocal rate radial flow interpretation of the same production data we've used previously. Download it from the site, work through this with me, and you'll get a good feel of how to do this. So the first step we want to do is create our reciprocal rate versus log of time plot. And so what we're going to do is we're going to overlay our data on this plot. I've already pre-formatted it, so all we got to do is calculate the reciprocal rate, which is 1 over rate of our data. So that's our our daily rate. I carry that all the way down. I have all my data points, and then I plot it on this plot, and it looks something like this. Okay? So if you recall, we have two flow regimes we're trying to differentiate. Infinite acting radial flow, which is represented by this straight line. So this equation is a straight line on semi-log plot because this is the slope and this is the intercept. The intercept is at the log of 1 because the log of 1 is equal to 0. And so this is a straight line. So we're going to plot this on our data right here. So let's go ahead and do that. And so what I've done is I've already put our parameters in here that we need. We need our slope and our intercept on this equation, and then I have our time data points that we're going to plot along this straight line just to overlay it on our chart so that we can do some petroleum engineering and try to fit to the early time data with this. And so I've put in a VBA function, and I'm calling it reciprocal rate straight line, and it's going to take those exact parameters. It's going to take our intercept, and you're going to want to freeze these, our slope, and our time produced. And so I'm going to carry that down, and you can see here's our straight line right there. And what I've shown with this triangle here is the time produced to the end of radial flow. So this is kind of the transition point between infinite acting and boundary dominated. And so if we go over here, we have our infinite acting region up to this point, and then we have boundary dominated. And so what you have to do to combine these equations is you have to use a little bit of coding logic, and it's not that intuitive, but it's not that hard either. And so the key points to remember are that when you transition from infinite acting radial flow to boundary dominated flow, what you have to do is you have to calculate an initial decline rate. Beyond this point, it's the same interpretation we did previously with rate time, the exact same equations. It's that, but this is the key point. You have to calculate your initial decline. Once you do that at this point, you're golden. And so what we're going to do is we're going to plot the combination of these two lines on our chart, on our interpretation here, and then we're going to try to fit that line to our data points. And so let's just go into the code to see how the coding logic is to perform this task. So if you press Alt F11, here we have it. So this is what we're going to plot on our reciprocal rate versus log time chart to try to fit to our data. And so what this function does is it calculates the rate using the combined infinite acting and boundary dominated. And so you have to use a little bit of logic to do that. It takes our slope, our intercept, the time produced in the radial flow, be boundary dominated, and the time produced. These are only the only five arguments we need. So if you recall, if our time produced is less than the time produced to the end of radial flow, then we're in the infinite acting region. And so here what I've done is calculate the reciprocal rate using the straight line equation right here. Or if you want to see it on this graph, this is a little bit easier to see right here. This is what that is doing. And so if you press Alt F11, you can get back to it. So I call this reciprocal rate straight line function right here. It's that equation, the intercept plus the slope times the log of time. and then I take the inverse of the reciprocal rate, because I'm going to perform a minimization of relative errors on our rate. So I just flip this value, I get a rate. If we're greater than the time produced to the end of radial flow, we're in the boundary dominated region shown here. If we're greater than this triangle, we're in Arps. And so recall that we have to calculate the initial decline at the end of radial flow. And so what I'm doing here is I'm calculating the initial rate at the end of radial flow, and then I'm going to, this is coming from our straight line, okay? It's just the rate at this point. Pretty intuitive. And like I said, guys, I'm going through this fast. Pause the video, work through it, you'll understand it. So I calculate the rate at the end of radial flow, and then I need to calculate the initial decline. So how do I do that? I just use this equation right here at this point. And I'm going to use the central finite divided difference to calculate that. So I go to my nominal decline radial flow function right here. And what I'm doing is I'm straddling that point by plus and minus, or a delta of 1. I calculate the reciprocal rate before the end of radial flow at one step back in time, and then I calculate the reciprocal rate one step ahead of time, and then I essentially take the reciprocal of that to get rate, and then I use that equation right there, the 1 over q times the derivative, and this is a central finite divided difference approximation of that derivative, and I get my initial decline at the beginning of boundary dominated flow, or at the end of radial flow. And so after I do that, it goes back up here, and then we calculate our rate using Arps. And so this is an equation we used previously, Arps rate. This is our rate time interpretation. Arps rate is going to be these equations right here. Okay? So what I'm going to do is I'm going to apply that function right here. I'm going to take out our error so that you guys understand the full extent of what I'm doing. So the function is infinite acting radial to boundary dominated decline. And so it's going to take our slope. You're going to want to freeze that, our intercept, our time produced to the end of radial flow, be boundary dominated, and the time produced. And something went wrong there, but be boundary dominated, freeze that, and then time produced. Bang. Okay, so that's the predicted rate by that equation with those values. So what I'm going to do now is I'm going to carry this all the way down to our last point. And then what you're going to do is you want to plot these on your graph. So you take the reciprocal rate, which is just going to be 1 over rate of your theoretical values. Carry that down to the end. And you plot it. Okay, there's our plot right there. Okay, so the next step we want to do is we want to minimize, well, we want to go ahead and calculate our relative percent error between our theoretical and our actual. So this is going to be our the absolute value, the same stuff we've done previously, of our actual rate minus our theoretical rate, divided by our actual rate. We want to carry that error all the way down. Okay. So there we have it, guys. We are prepared to go fit our function to these data points. And so what I want to do first is I want to get my end of infinite acting radial flow line pretty close to where I think it should be. So I'm going to go ahead. I need to increase my intercept. So let's do like 2. Let's go a little bit higher. Let's go to 8.0018. Okay. Now what I want to do is I want to increase our slope. So instead of, let's go to 3. Let's try 4. Okay, so that looks like a, it looks like it's going through our data points. 1, 2, 3, 4, 5, 6 data points. Those look pretty straight, and then it looks like it starts to curve. So guys, I want to warn you that this is an interpretation. It's really based on your knowledge, and you have to come up with the interpretation yourself. It's not a, click a button, let it run, and solve it. That's not the purpose of this. You actually have to put on your petroleum engineering hat and use it to create an interpretation that makes sense. In this case, that looks pretty good to me. That looks like a straight line. Your data may be skewed, and you may have to change your interpretation. Here it looks pretty straight. So I've gotten pretty close to where I want to be. And so now what I want to do is I want to apply solver and try to fit my boundary dominated flow right here to these last data points. So if you go to data, solver, I want my objective to be the error. I want to minimize the error by changing the parameters that are related to determine my boundary dominated flow. So I'm going to change the end of the triangle there, the end of radial flow, and the B boundary dominated. And so you can see, went through the data pretty nicely. Wow. So that's a good fit. But because our data looks pretty clean, I'm going to go ahead and regress off of all the parameters once, since I have a good fit right here, decent fit right here. Let's try to even minimize our errors a little bit more. This data is pretty clean. That's why I'm doing that. So I'm going to minimize my sum of errors by changing all these parameters: our slope, intercept, B boundary dominated, and our triangle there. And so we got a little better fit right there. It's slightly better. Went from 103% to 88%. I'm comfortable with this. I don't think there's any bad data points right here except maybe a couple. But that won't really influence our interpretation too much. Okay, so what we're going to do next is we want to determine reserves. And so if you remember, reserves, we need to approximate from the end of radial flow and beyond with a rate time interpretation, or Arps. So this is exactly what we're doing right here. The exact same thing we've done. We need our initial decline, initial rate, and then we need to determine our decline at this point and project it forward to the economic limit, or the economic rate. And so what I'm going to do here is our initial rate at the beginning of boundary dominated flow is right here at the triangle. So we've already determined the reciprocal rate at the end of radial flow, so I'm just going to take and divide that, take the reciprocal of that. That's our initial rate at the beginning of boundary dominated flow right there. Now I need to calculate the instantaneous decline, And so we approximate with that with a finite divided difference. I already wrote a VB function for that, and I called it nominal decline radial. Okay, it's going to take essentially our slope of our infinite acting region, our intercept, time produced to the end of radial flow, which is this point, and then our rate at the end of radial flow, end of infinite acting radial flow, which is right here. We just calculated it. So bang, that's our initial decline. So now what you have to do is, this is another key point. When you go from infinite acting to boundary dominated flow, you got to restart your time produced to 0 because you're approximating from this point beyond with a different function. So this is going to start at 0. So what we're going to do is we're going to forecast. In order to forecast, we want to take our last data point, right here. So we're taking our last data point right here, if you remember this, and project it forward. So it's going to be the maximum of our time data points here, last point in time. And then I have to subtract the end of radial flow, time produced to the end of radial flow, because I'm restarting my boundary dominated flow regime at this point. So that's how much time I've been in the boundary dominated flow regime right there. And so we're going to use our Arps rate to calculate our theoretical rate at this point. It's going to take our QI, initial decline, be boundary dominated, and then our time produced right there. So that's our last predicted rate right there. And so our instantaneous decline at this point is a function we used in our rate time interpretation video. It's going to take our initial decline, be boundary dominated, and our time produced. Okay, so we have our decline now at this point right here, our final point, which is also right here on this graph. And so now we want to project forward to our economic limit. And so we wrote a VBA function for that in the past. And all this code will be on my website. We called it cumulative production. It's going to take our initial rate, DI, be boundary dominated, and then our economic, will be an economic rate. So bang, okay, we calculate our reserves, check it out. So this is the same as the rate time interpretation, guys. The same process. The exact same thing as this. The steps to do this, we're duplicating it. And so here we have it. To calculate EUR, we just take our gas produced up to this point and add our reserves, and bang, that's our EUR. So check it out. That's it, guys. That's how you do a radial flow interpretation to predict EUR and reserves. And so if we compare the reserves of everything, we should anticipate that this would be less than our rate time interpretation. And so our reserves here are 376,000. Our reserves using rate time is 382,000, almost 383,000 cubic feet. But anyways, so if we compare reserves, I've gone ahead and plotted it here. So this is our radial flow interpretation. Our rate cumulative interpretation and our rate time interpretation. You can see here that our radial flow interpretation predicted less reserves than both of those. Okay, and the reason is because we have clean data. You know, we didn't, obviously this well wasn't shut in a lot, so it, you know, it's you know, it's been producing, looks like it's been clean data. And so, but what does make sense is that this is less than our rate time because this takes into account flow regimes. Because if I fit my data with the rate time to both flow regimes, this is going to be elevated. My B boundary dominated is going to be greater. And so that's going to lead to overestimating reserves. So guys, I mean, that's it. I know this was a long video, but guys, this is petroleum engineering. This is a smarter or a way to do things with more precision is to use these specialized plots. And what we're going to do in the next video, because we got our time produced to the end of radial flow right here, we can get a radius of investigation, predict original gas in place, and also we can get recovery factor and drainage area. And because we're using the straight line interpretation, we can also get permeability. So I hope you guys enjoyed the video. Please, you know, ask any questions you have. I really think this method of doing things is smarter than what you do with rate time and rate cumulative decline. But, you know, go back through the video if you're confused. I covered a lot of information, but it really is, if you understand this, guys, you're well on your way to being a rock star in petroleum engineering. And so if you enjoyed the video, please subscribe, and I'll see you next time. Adios.